what if there is a two-way relationship between x and y? So a change in x is associated with a change in y, and a change in y is associated with a change in x. What do we do? Then we have a simultaneous causality. Okay, so for example, we might have the system of equations. A system of equations is like several different equations which should be optimized at the same time. So we have the following, that y is dependent on x, and x is dependent on y. So for a unit change in x, then y changes by beta 1, and with a unit change in y, x changes with gamma 1 on average. Okay, so this is gamma. Okay, for instance, the problem here is that if we estimate equation 1, the y equals intercept times beta, or slope times x, then we will get a biased estimate of the slope, right? The beta. And the error term, the ui, becomes mechanically correlated with the x. And this is because the feedback loop of x depending on y again. Okay, that would be equation 2. So if we only estimate one of the equations, then we will get a biased estimate. And you can see that feedback effect. For example, if you have a positive nudge from the residual u, then you would have a positive nudge on the y. And if gamma 1 is positive, then a positive nudge in y would cause a positive nudge in x, which would feed back into a positive nudge in y again, and so on. So a positive nudge in u would then be positively correlated with x, right? And if gamma 1 is negative, then u and x would be negatively correlated. So in this case, you would have correlation between the dependent variable, the independent variable, and the residual, which would give you a biased estimate. And we can actually calculate this bias by using the omitted variable bias formula. So, for example, we just assume that the covariance, equivalently the correlation between the residual in equation 1 and the residual in equation 2, they are uncorrelated. Okay, so the probability limit of our estimate, okay, our estimate of this slope is equal to the true value of the slope, the effect of one unit change in x on y, and the bias. Okay, so this would be the bias term. And you see that you have the gamma 1 is per definition different from 0. Okay, it's per definition non-zero, because per definition the y has an effect on x, and the beta 1 is per definition different from 0, because per definition x has an effect, or is associated with a change in y. such that the variance of u is positive, right? And the variance in x is also positive, which means that this is valid. Well, this is valid for gamma 1 beta 1 different from 1, because if this product is equal to 1, then this term becomes 0, and the denominator becomes 0, and we get nonsensical results. So this and this product should be less than 1, because otherwise you would have this exploding relationship among the variables. So this bias is not equal to 0, which means that we get biased results of the slope estimates, because you can just make this formula for the second equation as well. So in this case, we assume we only regress y equals to beta naught plus beta 1 x plus u. Okay, and then you see that you get this biased estimate of the slope. Okay, and you can do the same for regression 2 as well. So this is regression 1. Okay, so we have inconsistent estimates, and the bias persists no matter how much data we collect. Okay, so a classical example is the simultaneous the relationship between supply and demand. Okay, the classical way to put this is like this. You have the supply and you have the demand, right? As price. I can't believe that. So the demand goes up if price is low, right? And the supply goes up if price is high, right? So, or you can have or you can decide the quantity. Okay, but if you have something statical like this, then you would have a quite easy life, right? Because this would be the equilibrium quantity and equilibrium price, right? But life is not that simple, because often you see only the price and quantity data like this, like points, right? And these points, they seem like random, right? And how can you estimate the supply function and the demand function from this, right? Then you have to just specify the demand function, specify the supply function, and there are many ways to do this, quite advanced, and then you have to kind of encounter the simultaneous simultaneity problem and try to estimate these equations based on your data. Okay, so that's a quite classical example of this problem, and the problem is that they are jointly determined, like price and quantity are jointly determined, which means that you can't really decipher or separate one from the other in a very easy way. So, what are the potential solutions to this simultaneous causality problem? Well, you can use instrumental variables. We'll look into that in a later lecture. And another possibility is to use a randomized controlled experiment, which is in most markets not viable, but in small scale it's sometimes viable.